So we've discussed a lot of sequences, and we've discussed limits of sequences, and we've discussed theorems that give us limits of certain sequences or combinations of sequences. However, we haven't yet seen the full definition of the limit of a sequence. We just had an informal understanding of what it meant, and via that informal understanding, we demonstrated that a reasonable number of things had a limit, and for some of them we were able to establish a calculation. Now it's time to actually fix the definition. So a sequence xn of real numbers converges to L as n approaches infinity if for every epsilon greater than 0 there is a whole number n such that when I take the absolute value of the difference, xn minus L, well, that will always be controlled by this epsilon for all n that are greater than or equal to that capital N. So it can kind of be confusing because there are a number of things in play here. There's the xn, there's L, there's lowercase n, there's capital N, and there's epsilon. And everything can be a little bit confusing. So it's good to have a story behind what is going on. In particular, convergence to a limit is an adversarial process. That means that someone can give me an epsilon to try and trip me up, and I have to be able to get my hands on this capital N for any epsilon that an adversary could pick. And once I have established that capital N, then I can guarantee that I have convergence. But remember that epsilon is always something that I have to beat. So it's a challenge when somebody says, here's an epsilon, find an N that works. A simple example. Let's claim that the limit as n approaches infinity, n over n minus 1 is equal to 1. Now, of course, we can't really discuss this when n is equal to 1, so we just assume that n is 2 or greater. And using a little bit of algebra and our limit theorems, we can already establish that this limit does exist. But let's try to use the definition. So for example, let say somebody who doesn't like me, they say, oh, pick a really small epsilon. That means that it's really hard to get this number really close to 1. So let's say epsilon is 0.01. That is 1 over 100. Well, somebody who's my adversary gave me this. What n will satisfy the limit requirement? Well, remember that the limit requirement is, well, for all lowercase n greater than or equal to n, I'll have to have that xn minus L is less than epsilon. So in our case, let's substitute in all these values. So in our case, we've got that xn is given by n over n minus 1. and L is given by 1, and this is less than epsilon. In order to prove that the limit exists, we generally have to reverse engineer n given epsilon, and we reverse engineer it in terms of the lowercase n here. So now let's work a little bit on the algebra here. So I have n over n minus 1 minus 1. Well, that'll be n. When I multiply by a form 1, 1 will be n minus 1 over n minus 1. So I've got minus n plus 1 over n minus 1. Now this is the inequality that I want to hold. So now I've got 1 over n minus 1 will have to be less than 0.01. Well, now this is positive, and so this is now equivalent to 1 over n minus 1. So it's good to go back and establish that in fact we haven't changed anything. So this is the same as this line. This is the same as this line. This that I'm about to write is the same as this line. So now this number on the left is positive, and so I can multiply both sides by n minus 1, and I can multiply both sides by 100 to cancel out this part. So I multiply everybody by 100, that is both sides of this inequality, by 100 times n minus 1. And what do I get? Well, I'll get 100 on this side, the n minus 1 will cancel out, is less than, and over on this side I'll get n minus 1, because the 100 will cancel out here. And this was also equivalent. I can always go backwards from this step. And now finally, I add 1 to both sides, so I get 100. 1 is less than n. So now I want to figure out what capital N is. So I know that this inequality will definitely hold. The previous inequality, that limit inequality, that's important, will hold so long as n is strictly greater than 101. So therefore, since n greater than or equal to 102 implies n greater than 101, which we've shown is equivalent to xn minus L being less than the epsilon that we chose in this case. We have n equal to 102. Now we've done this for one epsilon. For one epsilon, I've established that capital N can be 102. But now the game gets a little trickier because we have to establish this not for that epsilon, but for every single possible epsilon. And so we generally just say, well, let epsilon be greater than 0, indicating that it's some arbitrary quantity, but it's definitely greater than 0. Well, now we have the same system of inequalities, and the derivation, where now we have epsilon instead of 0.01, leads us to 1 over n minus 1 is less than epsilon. Or equivalently, 1 over epsilon plus 1 needs to be less than n. Well, this over here is some positive natural number. Or, well, it's not natural, it's a real number. And in particular, we take the ceiling of this, so the largest number here. So if we set capital N equal to the ceiling, so ceiling is denoted by this little ceiling of a number. So this is going to be the smallest whole number that's greater than or equal to 1 over epsilon plus 1, then n greater than or equal to n implies well, technically we'll have to do plus 1 because we want to be strictly larger than this number. And technically this could have been a whole number to begin with. And so this will imply that 1 over epsilon plus 1 is strictly less than n, and hence xn minus that L that we want is less than epsilon. So now we've found a candidate for any epsilon. Somebody gives me just a any epsilon that will do, and this now works. In particular, this capital N is a function of epsilon, and so it tells me exactly what n I need to get whenever some adversary gives me an epsilon that guarantees that my sequence is within epsilon of the limit.